Module 2.1. We've got more than anything else, we've got some terminology and some big ideas to go over today. Some of them can be a little bit tricky, but let's talk about domain. Has anybody heard the term domain? Anybody know this? No? Or you think so?
I said, yeah, I think so, but not in context of math.
Okay. Yeah. So, I mean, in not in context of math, this room is my domain, right? Okay. Yeah, that would be more of like an English context. It's my zone. It's my it needs a paint job. It needs some color, but my domain is what it is. So, actually, if you guys can work out getting a skylight in this room would be awesome, wouldn't it? So, I don't really, so what if the class above us has to like look around something to see what's going on the board? That doesn't affect me, right? So let's have a skylight. That's all I'm saying. Okay, domain, this is simply the set of x values. Mm-hmm. The x values are your independent set of values. So let's say the x's are your independent set of values. So if you have a context where you have to decide what's the x and what's the y, in math, time is so regularly the x because it's something that you can count on. It's something that's regular. It's something that happens without you doing anything. It's just going to occur. Bless you. Let's talk about a little bit different situation. What if I'm looking at prices of crude oil versus prices of gasoline? Which one comes from the other? Do you get the crude oil from the gasoline, or does the gasoline come from the crude oil? Does anybody know? Correct. Gas comes from the crude oil. So if I was looking at prices of crude oil versus prices of gasoline, which one would be the independent variable that which one leads the other, I guess is another way of saying it? The crude oil, right, exactly. In that case, crude oil would be your independent set or your independent variable. The independent set is always your left-right. It's your horizontal axis. And if you don't know this, they refine crude oil into gasoline and among a lot of other things. But generally, the more expensive the barrel of crude is, the more expensive gasoline is. All right, so the range is the set of y values. They are the dependent set. In my example, gasoline price is dependent on the oil price, the crude oil price. It doesn't go the other way. This is your vertical axis. You might say the range is what you're studying. So domain and range. So if I gave you a graph, just a real simple graph, we'll go 3 in each direction. So here's my x and here's my y. And let's say I have a graph that starts here and ends here, and it's connected in some sort of weird curve, perhaps. What is the domain of this graph? What are the x values that exist in this graph? Here's how you can check it. You can kind of, let's see, do I have a card here? I do. Here's my joker card, okay? So for the x's, I'm going to take and I'm going to make this a vertical, it's a vertical line, and I'm just going to drag this card across my graph. When do I touch the curve? Right there, right? What is the x value where I touch the curve? -1. Okay, so the domain starts at -1. And as I'm dragging this across, when do I quit touching the curve that I drew? At 2, right? Okay. Now, we're going to talk about some notation on this, but another day. So the domain is from 1 to 2. That's not entirely the best way to write that, but we'll deal with that another day. How about the range? The range is the up and down. So if I take my joker card and I go up, when do I touch the curve? At 0, right. And when do I quit touching? At about 1, right? So the range of y values is simply 0 to 1. That's domain and range. Think of it as taking a walk along the x-axis, taking a climb up the y-axis. Where do you find the graph? What if it doesn't look like that? What if it does something like this? I'll do the same x and y, 3 in each direction. What if instead of a line, I have just points? Now, what is the domain? As I drag my vertical line, my joker curve, my joker line across, where do I touch? At -1. Is there anything between -1 and 0? So where do I touch again? 0, right? I'm looking at the x-axis. And I touch again at 1. And then I touch again at 2 and 3. Now, this one I am going to give you some notation on. We use ellipses to indicate that this is individual sets or individual values. So the domain is just 1, 0, or -1, 0, 1, 2, and 3. Not all the values in between. no fractions at all. It's just the points. How about the range? I'm coming up. When do I touch? At 0. Now, I touch 0 in 3 places, but I don't need to list all 3 places. Only the 0 once. And then I go up again, and where do I touch again? 1 and 2. Domain and range. These are the values of x and y for this set. Does that make sense? All right, now what I've drawn is a couple of totally different situations. One where there's individual points that we don't have or can't fraction up, and one that's a line where I could use fractions, right? Can anybody think of a situation where you can't cut something in half? Something cannot be cut in half. Yeah?
0.
Okay, you're thinking mathematically, and I'm thinking object-wise. Step out into the real world for a minute. What is something that we can't cut in half? I can think of something. Yeah?
Planets.
I don't know. Do you think with a big enough bomb? Star Wars, they fractioned up the Death Star pretty well.
Well, we're talking.
You're right. You're right. Okay, you can't do planets. How about people? Oh, yeah, you have a question or an idea.
You can't cut air.
Can't cut up air. Well, you can in science. They can break the hydrogen and the oxygen apart, but it takes more energy than what it gets. Yeah, so I mean, I guess scientifically you could. I'm thinking people. Like, it's, you can, but it's not really socially acceptable. So, if I brought a chainsaw in and did a demonstration where I started the chainsaw up and I cut one of my students in half, right, to demonstrate half, that probably wouldn't go very well. Would you agree?
Well, you can still do it.
It could be done, but is the person still a person at that point?
They're a dead person.
Yeah, but I think their existence is sort of ended, right? Then they're just worm food, okay? Right? I could use that demonstration. So there are some things that you can't have. So when you guys come walking into the room, as you walk into the room, we don't count that as, let's see, there's a 0, and then, oh wait, there's a quarter of a person, they haven't entered entirely. No, we don't do that. It's like there's 1 person, 2 persons, 3 persons, 4 persons, they're entering the room. We don't consider people in terms of halves. Even if there's a horrible accident and all your arms and legs are chopped off and you have no arms and legs, are you still not a person?
You're a robot.
No, you're a person, you just don't have any arms and legs, right? You're a little lighter, perhaps, than you were, okay? But you're still a person. So, we can't really have people. That's a discrete situation. Discrete models use numbers, or use, yeah, let's use numbers, that can't be fractioned. Trying to think of an example where you can cut something in half, but you can't cut it into quarters. Anybody think of? Yeah, I can't think of. You can still have a discrete situation with like halves or quarters or something like that, but you can't cut it into smaller fractions. Maybe a penny is a good example. A penny is a fraction of $1. But can we fraction that is the value that can't be fractioned, right? You can't make it a fraction any more than what it already is. So discrete models use numbers that can't be fractioned. They just occur as points on a graph. The points are not connected. Discrete situation could be something like, simply like this. Points on a graph that can't be connected. They may very well have some relationship, but the context makes it so that you don't really talk about parts. So, all right. How about another idea? Continuous. I probably shouldn't say numbers here. I'm going to change this. I don't like the numbers here because it doesn't leave enough room for context. Now, let's say values. How about that? Even that leaves me a little uncomfortable. Continuous models are something where you can fraction it. A great example of a continuous model, and I think you'll see in your work today, is what if we are filling a bathtub? You don't fill a bathtub by taking gallons of water, heating them up, and then going and dumping them in one big chunk, right? You don't do that. You could, but you don't, right? You turn the faucet on, and it runs in continuously. So the height of the bathtub changes in a continuous linear model of some sort. It's probably not totally linear, but continuous models have values that can be fractioned, or use values that can be fractioned. The graph is continuous in that the points are connected. Oops, sorry. Perhaps it's a curve, perhaps it's a line. Perhaps it's some wacky thing, we don't know, but it's connected, it's a line. It's a series of points that are so close together that they create a line. So maybe as an example, counting students entering a class, and this one could be filling a bathtub. is used for discrete models. X is used for continuous models. So when you see n, if the writer of the problem wrote it correctly, what they're indicating is that it's a discrete model. So, ice cream flavors in a shop. How many ice cream flavors? You can mix ice cream flavors, but you can't really buy mixed ice cream flavors, I guess is maybe a way of thinking about that, unless they create a new flavor. But if you're talking about ice cream flavors, you'd probably be using N. If you're talking about, I'm stuck on the filling a bathtub, filling your swimming pool or bathtub or something like that, then you're using X. Can you connect the points, or does it make no sense to connect the points? Okay. So N and X distinguish between those two. All right. Any questions at that point? That's hitting you with a lot of information. I think it'll take us quite a ways, though. Let's